This video goes over a synthesizer module I just recently completed based around an LM567 Tone Decoder chip. I'm going to talk a bit about the design, how I built it, and then I'm going to demonstrate it in a few different examples, both as a triggering device and as a timbre extender. The 567 is an 8-pin linear integrated circuit that was developed by National Semiconductor in the 1970s. Its primary applications were in things like touch tone decoding, some control applications, different kinds of scenarios where you had to detect a particular frequency that was present in a signal. The chip pretty much went obsolete in the 1980s and 90s when you had other devices that were more stable or better suited to their applications, as well as all digital implementations of these functions, but you can still find them around. But the 567 is quite a useful functional block in that it does have an integrated voltage-controlled oscillator plus a phase detector. It essentially implements a phase lock loop in its detection. By specifying a couple of resistors and capacitors, you can dictate the frequency range over which a detection is made and how the internal oscillator will respond to the input signal. I was already using this chip back in the early 1980s. Here you can see a circuit I designed to detect touch tones for the intercom system I made at the Tufts University radio station back then. So I pulled out one of those chips that I had around, threw it on a proto board, and started experimenting a bit to see the different things I could do with it for synthesizer applications. I then roughed out a little circuit that I could build to explore using this chip in synthesizer applications of different sorts. I then designed a front panel for this circuit that let me adjust all of the relevant parameters for this device, as well as put signals in and pull signals out at many relevant places for this chip. I then made a layout that enabled me to pack all of the switches and connectors and potentiometers onto half of a standard synth panel. This lets me pack 2 of these devices into one module. And of course, I drilled it out by hand. I'm only planning to make one of these modules. The module at the right actually is a 6-channel line amplifier that I've also recently built, but that's another story. And here's the finished panel, lettered with all of the front panel components mounted on it. And here you see the hand-wired circuit board with the 2 tone decoder circuits all wired up to the front panel. And my cat Kumo really loves that power supply wire that hangs from the back. And here's the tone decoder module mounted in my synthesizer and ready to go. In this first example, I'm just sweeping the frequency of an oscillator by hand, inputting a triangle wave from that oscillator into the input of both tone decoder channels. The 2 tone decoders are adjusted to different frequencies. When the VCO frequency reaches the frequency that the tone decoder is set to, it will produce a gate that will trigger an envelope generator. The upper tone decoder is set to a higher frequency, lower one is set to a lower frequency. The envelope generator feeds a VCA that allows the oscillator to pass into either an echo or a reverb or a timbre modifier. So you can hear different effects come in when you pass or when you're on top of the trigger frequency and the tone decoder activates. Here I'm controlling the frequency of my VCO with a smooth ramp, and when it passes a frequency that the tone decoder is set to respond to, it will produce a gate that will again change the timbre of the signal at that point. Here I'm adjusting one of the tone decoders to respond to a slightly higher frequency. Of course, you can also put a signal from a keyboard into it. Then you can program the tone decoders to respond to certain notes. In this case, I have it responding to the middle 2 C notes, so it responds to a subharmonic as well. So it gets also the lower C. I have the other tone decoder here set to respond to the lower E flat, where it brings up kind of a mellotron sound and some more ambience. It also responds to hearing its programmed note or a related tone in complicated chords. If I pull out an intermediate signal, for instance the loop voltage, and dial back the filter time constants in the tone decoder, it produces some incredible crunchy timbres. The phase lock loop tries to lock on to a signal. It works in certain octaves. If you're too far out of range, it keeps trying. Sometimes it gives up and is intermittent, or makes some beautiful noise, or produces a gritty subharmonic, or does some strange kind of beating. Every note is different, and it depends on how you go to that note. The keyboard kind of comes alive. In this example, I'm controlling a standard VCO from the keyboard, and the triangle wave from the VCO is going into the tone decoders, and I'm taking the output of each tone decoder to a different audio channel. One's going to left, one's going to right, and in the center you can hear a small amount of the original signal that they're both tracking. I can also change the characteristics of the oscillators and the tone decoders so it responds in a different way at different frequencies, essentially changing the range in which the phase lock loop can actually try to grab the signal. The effect is like a divide by n natural scale or a synced oscillator here, but the noise in between the different lock modes is just wonderful. Of course, I found a way to voltage control the internal oscillators on these tone decoders. So here I'm using the two controllers at the top of my keyboard to modulate the oscillators independently. You can really rock out on this one. In this mode, if I switch the frequency of my keyboard up an octave or two, the tone decoder just wants to screech. And here, as I vary the pitch of the input oscillator, you can hear the tone decoder go through lots of attempts to try to lock onto the signal at different octaves and range of pitches, giving lots of interesting sounds along the way. And here in my last example, I'm driving the oscillator input to the tone decoders with a sequencer, and I'm varying the control voltages for the tone decoders periodically. So the pitch of the internal oscillator in the tone decoders is changing dynamically. After the note attacks and begins to sustain and then decays, I feed it into a really nice Lush Reverb. This example develops quite a beautiful haunting sound, so I'll let you guys, again, dream out on this one, and this will take us to the end. Thank you very much for listening.